have seen a lot of applications of them, how you can even explain some brain data, both not only behavioral data, but also in actual brain data, like from what you get from fMRI and electrophysiology and all that. So now we look at a more general class of networks called Hopfield networks. These are examples of recurrent networks, which can be used to model memories in certain sense. So also people have found some analogies between these kinds of memory models and holograms, and also magnetic materials. So I just want to mention that and show that in the title. So we will look at initially the binary model of Hopfield network. We look at update equations and there's an energy function, right, which is like the error function that we used in the MLP. Then we'll talk about Hebbian learning and how it is relevant, how it is seen in real synapses, real brain connections. And we look at the concepts of attractors. What is an attractor? And what is the relationship of that to memories? And so there are lots of applications, and there are also some problems with this model, and there's some extensions, right? So one of the extensions we look at in this series of talks, in this part of the course, is we'll extend this through a series of models and go towards a model of hippocampus. Hippocampus is a part of the brain which is involved in memories, or specifically a kind of memory called declarative memory. So these are kinds of memories that you can declare or express, often in language. And so, for example, here again you have two subcategories, episodic and semantic. So these are like memories of facts or memories of events. Hippocampus is crucial for retaining these kinds of memories. It is most essential for consolidation of memories. That is, when you memorize something, let's say you're cramming for an exam, you store it temporarily in hippocampus, and after that you pass it on to long-term stores in the cortex. Now, so there are a lot of models, models of hippocampus, right, can be traced back to a very simple recurrent network. So where the connections are, the neurons are connected all to all among themselves. And Hopfield network is an example of such a network. So we'll come to that. Now, these recurrent connections or reentrant connections, right? Connections of neurons among themselves, right? These are very common in the brain. And so what we have seen so far is feed-forward connections. That is, you have a series of layers projecting in a sequential fashion, each to the next one. Okay, and then you have input given to the input layer, then output picked from the output layer. You can have inputs coming randomly at any level, but the only condition is that there should not be loops. So if you follow these arrows, because each connection has an arrow, information can propagate only in that direction. So if you follow these arrows, you should not find any loops within the network. Then it's called a feed-forward neural network. Our deep networks are examples of that. In a recurrent neural network, you can have loops. So that's the most general neural network. So you can have loops, for example. Okay, from here you can go here. That's an example. Okay, but specifically in a Hopfield network, we are looking at a bunch of neurons, where every neuron is connected to every other neuron. So among themselves, you have connections, and so on and so forth. So you'll have totally n square connections or n square minus n connections if you ignore the self connection of each neuron. So these kinds of recurrent connections or reentrant connections, both mean the same, are very common in the brain. And in the brain, very often you will find that if a region A, right, projects to region B, and then region B very often returns those connections. So these are called reciprocal connections, like A to B and B to A. These are called reciprocal connections. These are very common in the brain. So therefore, networks which have loops in them are more natural, more brain-like, rather than networks which have only feed-forward connections. But networks with feed-forward connections or feed-forward networks are easier to analyze, easier to train. So that's why you start with them and slowly move on to recurrent connections. So now Hopfield network is an example of a recurrent network, and specifically it has a special connectivity where every neuron is connected to every other neuron. If it has n neurons, then you have this n square minus n connections. And now the beauty of this model is that it can be interpreted as a model of human memory, or specifically a kind of memory called an associative memory. Okay, and what is an associative memory? And we know what memory is, but what is an associative memory? So let us look at that and compare with the kind of memory that you see in a computer. In a computer, the memory that you have is what is often called an index memory. That is, you have in a computer, if you want to fetch some information, right? You have a bunch of indices, so the addresses, right? And then if you go to the address, right, and at that point you have some content, and you can read out the content. So without having the address, you can't get the content. So it's kind of like what you have in a library. So in a library, if you want to find a book, you need the call number. You trace following the call number, you go to the correct racks or stacks, and then you find the book. Therefore, sometimes we play games, we play some pranks, and misplace the book, put it somewhere else, and you can't trace the book anymore. The book is practically gone. Right, that's how index memory work. You need the address to find the content. But that's not often the best way to organize information. Take, for example, the case of telephone directory. So now you don't have telephone directories per se. They're not at least common. I mean, in the institute you still have telephone directory, but outside you just you get onto the net and you can find information. But there was a time when people are using telephone directories. So the way they're organized is so for every name, which is organized as last name first and then first name, you have the person's telephone number and the address. So it's a list, basically, the name or especially last name, then followed by first name, then address, and then telephone number. So if you want somebody's telephone number, then you have to know that person's full name, last name and first name, and then you can get the address and telephone number. But consider these other possibilities. You know somebody's address, right? Let's say you're a detective, and you know that somebody suspicious is living in certain address. You want to find out their phone number, right? You can't do it with a traditional telephone directory. Or you have written somebody's number, you jotted it down quickly after a telephone call. You jotted down the person's number on a piece of paper. Now you forgot whose number it is, right? So given the telephone number, can you trace to whom it belongs, right? It's not easy with a traditional telephone directory. So ideally, if the memory or the database is organized like this, you have set of names and addresses and telephone numbers. So given the name, you should be able to get the telephone number and the address. But also given the telephone number, you should be able to get the name and the address. Or given the address, you should be able to get the names and telephone numbers. So the information should work in all directions, right? So the whole thing is a record. This combination of name, address, and telephone number, the whole thing is a record. Given any partial set of this record, you should be able to pull up the complete record, assuming there is a sufficient uniqueness. Like for example, if you have only street name, that's not unique enough, so you might get half a dozen different telephone numbers. So that's not unique enough. So this kind of an address is called an associative memory because you organize this memory by association of a name and an address and a telephone number. And this is very often how we store information because if you want to recall somebody, if you want to recall somebody to somebody else, you say, hey, do you remember that person we met last year in some hostel day? Then guy asks, no, who is this person? Oh, he was wearing a weird dress and he was wearing a yellow shirt and red pants or something. Yeah, I know, I remember that guy's name is XYZ and he studies XYZ. So the thing is, you learn things by mapping A onto B, B onto C, by creating a network of items, right, in which each item is connected to or associated with other items in that network. So brain memories work like that, and so therefore you can give a partial information about a whole, right, and then retrieve the whole. So here you give only the partial information of this Mona Lisa picture. You can retrieve the picture. That could be eyes or mouth or even a little corner of the head, right? Might be enough if you suppose you are art buff, and just by looking at this part you can say, hey, that's Mona Lisa. So that leads us to the concept of an auto-associative memory, where you map an input onto itself, or rather, you map maybe an incomplete version of the input, right, onto the complete version of itself. And that's not associating a memory or a vector onto itself. Whereas in a deep network, we map an input onto something else. Okay, there is something called autoencoder in a deep network. I didn't talk about that. I'll skip that for now. So Hopfield network is a model of auto-associative memory. So where I give an initial input X, right? You can think of it as incomplete pattern like this partial Mona Lisa picture. My objective is to retrieve the full Mona Lisa picture. So when I give this partial picture, imagine that I have this remaining thing, which is all empty space. Right? Imagine it's all zeros. Okay, and then when I give this to the network, it should crunch through it and then return the full image where the empty parts are all filled. So that's what the Hopfield network does, and it does it by some kind of a recursive process. So you give this incomplete pattern, or you can think of it as a noisy pattern, so which is initial state, call it X naught, and give that to the network, and network works on it through multiple steps, generates a series of them, X1, X2, X3, and so on. And after some time, when X converges, it returns this Xt, right, at some sufficiently large T, right, and that is your final pattern, the complete pattern. Now, this aspect of an associative memory, where it is able to take a partial piece of the memory and then return the complete thing, caught the attention of a psychologist called Carl Prybram several decades ago. And he proposed, and he also saw an analogy between this property of memory and holograms. Okay, and Carl Prybram happens to be the student of another scientist called Carl Lashley, right, who studied animal brains for a long time to study how memories are stored in the brain. He called that imprint of the brain in memory, he called that an engram. So that's just a word that represents how information is stored in the brain. So people initially they were thinking that information is stored specifically in specific locations, like just as the way you store documents in a file, right? Specific files in specific cabinets. So that's what people thought. That's how people thought memories were stored in the brain. But it didn't turn out to be like that. So memories seem to be more distributed in the brain. Everything seem to be stored everywhere, which is very confusing. So Carl Ashley's experiments didn't turn out to be very conclusive. So it was not very satisfactory. The findings were not very satisfactory. So one of his students, Carl Prybram, right, continued that pursuit, the pursuit of his teacher. And Prybram's son happens to be a physicist. And just about the time in the 60s, the holograms were discovered or invented. You can say it whichever way. And then his son was telling his father about holograms and the physics of holograms and so on. Immediately, Prybram saw a connection between holograms and memories. Why is that? Let us look at that a little bit. Because holograms are like 3D like display of objects. That's where you see, you can. So normally, when you look at a picture, you can see it clearly only if you see it straight on from the front. If you move to a side, it will look compressed, and if you move completely to one side, the picture disappears. Whereas if it is 3D object, when you move to a side, you will see the object, but from a different aspect, right, from a different angle. So that is a kind of a impression that you get when you look at a hologram, which is like a 3D display of an object. Now, the holograms in popular media have become very popular with Star Wars, among other movies. Because in the late 70s, when Star Wars first came, all these flash pictures of Princess Leia appealing for a rescue, right, through a hologram projected by R2D2. It was it created a lot of buzz and people went crazy about it. So holograms really caught attention, popular attention. So these holograms are they depend on this concept of interference, light interference. So we know that light is a wave, right? From our school days, we know that. And waves interfere, and there are two different kinds of interference. Consecutive interference, where waves add up and produce a larger wave, or destructive interference, where waves cancel out each other and produce nothing. Right. So, and we also know this double slit experiment, where if you have a plane wave impinging on a single slit, S0, and then it becomes a circular wave or a spherical wave. Then spherical wave impinges on another pair of slits, S1 and S2. So where so out of these slits you have two spherical waves emerging, and these two waves interfere with each other. And if you have a screen right on the other side, the waves impinge on the screen, and the interference pattern of these waves can be captured if it is a photographic film. And you'll see a nice black and white kind of band structure, and you can calculate the intensity distribution and the thickness of this band. Now that you have done some of this even in your high school for your JE. Okay, so based on this principle of interference, you can construct a hologram. You can construct 3D pictures of objects. So how do you do that? So you take a coherent beam which produces a light wave, right, a monochromatic beam, and you have a beam splitter. So where is some kind of a glass through which it partially allows the radiation to go through and partially reflects it. So the beam that goes through the beam splitter goes forward and falls on an object, a real 3D object, and gets reflected. And so these waves bounce off the object and go to one side, right? And so the thing about this reflected waves is that the phase of these waves is distorted by the shape of the object. Right, whereas you have another beam which is just reflected by the beam splitter once, and then you have a mirror on the other side, and again these waves are reflected. These waves are still the same, planar waves, the coherent light beam. So the reflected beam, which is called the reference beam, it then interferes with the beam that is reflected off the object. We call it the object beam. These two beams interfere and leave the interference pattern on a photographic plate. So now when you flash another coherent beam, which is called the reconstruction beam this time, on the same photographic plate which you just created here. So when you look at the beam that goes through the photographic plate from the other side, you will see the original phase pattern of the 3D object. So the kind of phase pattern that you saw, right, coming off the object, you are now able to reconstruct it. So that's the reason why you are able to see it as a 3D object and not like a flat picture on a paper, right? And that's what a hologram is, this reconstruction. So the nice thing about the hologram or a picture that's generated like this by this process compared to a photograph is very interesting. So if you have a photograph, you take a negative of the photograph. Let's say what you see on so this is a negative, right? And then you develop it. So this is a positive or the developed photograph. Now in the negative, you distort some part, you remove some part, right? And then you develop it. So you'll find that part will alone be missing, right? And then the rest of the picture is intact. Whereas if you distort a photograph, so this is a proper proper hologram. Now you take this the holographic film, maybe, and damage a little part of it somewhere, and you reconstruct the hologram. You won't see a local damage like what you see in a developed photograph, but you will see the whole thing degraded, right? So the local damage is distributed, and you see the whole picture. So what that means is the entire information about the whole image is present everywhere in the hologram, little bit. So therefore, if you damage a little bit of the hologram, the holographic film, the reconstruction, the whole image is damaged a little bit, but not, you don't see any partial missing pieces. Okay, so the manner in which the whole is stored everywhere is something very peculiar about a hologram. And that seems to be the kind of a mechanism or a process that you need to store brain-like memories. Okay, so so based on that, Carl Pribram proposed what is called a holonomic brain theory. This is way back in the late 60s. And that became very influential. People actually even found, neurobiological evidence that those kinds of waves and interference patterns are present in the brain and the axon, so the output of the axons. or create waves like that, and so on and so forth. But in the 80s, Hopfield has proposed a much simpler model, because the holographic brain theory is inspired by the physics of holograms, and therefore it depends on optics, and you have all this this wave equations and all that. So it's fairly complicated. So Hopfield has proposed a much simpler model, based again on our good old McCullough-Pitts neuron. He has taken the same neurons and constructed a kind of a recurrent network out of them. And Hopfield has shown how such a network can have memory properties. Okay, so let us look at that. So in a Hopfield network, you have a bunch of neurons, let's say n neurons, and in which each neuron projects to every other neuron. Okay, so if you accept it's a kind of a self loop also, then you have totally n square connections. So because your weight pattern or weight matrix will be a matrix, right? Where ith neuron, the connection between ith neuron and jth neuron is the ijth entry of the matrix. Now, so thing is, so if you take the ith neuron, and the state of the ith neuron will denote by vi. So the notation is slightly different from what we use in case of MLP or deep network. So vi is the state of the ith neuron, and it will take two values. Vi is in the set +1 or -1. Okay, so we're not using 0-1 convention, we're using 1-1 convention. And it's again the same McCullough-Pitts neuron, but the only difference is that the nonlinear function is not the step function, but it's a sine function. So how does it work? Vi is equal to, we'll use the nonlinear function sigma, the notation is sigma, and sigma j wij vj. So vj is the state of all the other neurons, right? So you add up, take a linear sum of the vj's. So this is vj, and this is wij. It's connection from j to I. So there's a direction to each connection. All right, and you sum up all that and it passes through a sigmoid function, this sigma, and that's output vi. And sigma is the sine function or the signum function. Okay, so we know the definition, right? So is equal to +1 for x greater than or equal to 0 and is equal to -1 otherwise. So this is the equation, and so there's one thing that we should notice about this equation. So we have vi is equal to vi is equal to sigma wij vj. Now, one weird thing about this equation is, so when we take the sum of all these states and pass them through the weights, multiply through the corresponding weights, add them up, and pass it through a sigmoid, the signum function, you get vi. But point is, you see that vi is present both on the left side of the equation and on the right side, right? So what does it mean? It doesn't make any sense. So to break that tie, we need to introduce time into the equation. Okay, so what that means is, take the state of the network at time t, and then do this calculation that you see on the right side. And the result of this calculation gives you the state of ith neuron at time t+1. So that's the only way you can interpret this, because the moment you have a loop where x influences y and y influences x, to make this calculation possible, you need to bring in time. So which comes first, which comes later? You can only represent this some kind of a recursive process evolving through time. So that's what we do here. So the equation, the expression on the right side is calculated at time t, and that gives you the state of the ith neuron at time t+1. So because of this process, right, you have a recurrent process. So that's how you calculate this. And because of this, the state of the network evolves through time. So this is quite different from the way an MLP works or a deep network works. In a deep network, right, you have a bunch of layers. The input is given here, and it immediately, instantaneously goes through all the layers, and you get the output Y. There's no time gap between input and output. Whereas in case of a Hopfield network, right, you have this bunch of neurons. They're connected to among themselves completely. And you start the network at some initial state. I'll call it V naught. So V naught gives you V1, V1 gives you V2, and this keeps on evolving through time. So this is quite a different kind of a network just because of the presence of loops. Okay, so now the thing is, as V evolves through time, what happens to it? I mean, does it converge? Does it stabilize somewhere, or does it just keep wandering the state space? Because what is the state space here? Vi is plus or minus 1. So that means, so Vi just is jumping from, each component jumping from 1 and minus 1. So that means if you look at an n-dimensional vector, right, take for example the case of n, so number of neurons is 3. Okay, the different states can be represented as the different corners of a cube. Okay, so as you keep updating your neuron states, you are basically jumping from one corner of the cube to the next corner, maybe in that corner, okay, and so on and so forth. So will this process ever stop? Right, once it reaches a certain corner, will it stop, or will it keep on hopping? Okay, so that's one question. Then a network like this, whose dynamics is described by an equation like this, how can it be a model of memories? Okay, so let us first look at an intuitive picture of this. Maybe let me make an extra slide. Okay, so you have a network where the state of the network changes through time and evolves through time. How can you make it behave like a model of a memory? So we have seen that. So we have seen that this state V, initial state V, evolves through time like this, V1, V2, and so on. So which means we start from some point in the state space. Okay, after that, I jump to another point. After that, I jump to another point. So I keep on moving like that. Now imagine, so let us say I have some theorem or some mathematical property of the network, which assures that no matter where I start from, I'll always converge after some steps. So that means, and I follow a trajectory, and after some finite number of steps, I go to a point, and after that, I remain there. That means Vt plus 1 is same as Vt for some, for t greater than some capital T. Let us say I give some result like this. Then it goes and stops at some point. But is there some unique stable state, equilibrium state, right, to which all initial conditions go to? Okay, then that will be pretty pathetic, because then the network won't be doing anything interesting, right? So, but let us consider a different situation where from different initial conditions, the network goes to different final states. So for example, if I start from here, I land here. If I start from here, okay, I go through a bunch of steps and I land here. If I start from here somewhere, I go through another bunch of steps and land here. Okay. So you get the picture, right? Now, thing is, obviously, if for every input, it cannot go uniquely to a different state. So then that will also be useless. So imagine a situation where from a bunch of inputs, right, from a large number of initial conditions, the network goes to a smaller number of final equilibrium states. So something like that. Okay, so my initial state, the space of initial states is much bigger than the states of set of final states, right? Um, so if this is how the network behaves, right? Suppose we guarantee that this is the kind of behavior you'll get from the network. Then you see that it's doing something very interesting. So if I am starting from anywhere in this part of the state space, the network will go to this state. I'll call this state number 1. If I start from anywhere in this part of the state space, network will go to state number 2. Somewhere in this part, it will go to state number 3. And somewhere in this part, it will go to state number 4. Okay, so let us think of an imaginary network where no matter where you start from, you'll go to one of these 4 states. Now you can think of it as a memory network. Right? You can interpret what is happening in the network as some kind of memory, because let's draw a simpler picture. Right? Let us say I'm dividing the whole state space into just 4 regions. All these points, right? If you start from any of these points, you go to state 1. Okay, so if you go to from any of these points, you go to state 2. From any of these points, you go to state 3. Any of these points, you go to state 4. So you have divided the entire state space into 4 partitions. Right? Now you think of these 4 states as 4 memories which are stored in the network. Why is that? Because if I start from anywhere here, I land here. And so think of any of these points from which you are starting as some kind of a incomplete versions of this state, or noisy versions of this state, because all these points are somewhat close to this state number 1. So therefore, you can think of all these points as incomplete versions of state 1. So therefore, if you start from any of these points, you'll end up in state 1. So this is similar to our Mona Lisa example, right? So where you start from like a partial picture of Mona Lisa, and you get back the full picture of the Mona Lisa. You can start from any partial part, right? I can take only the forehead and get the full picture. I can take only the chin and get the full picture. So all of them are sufficiently close to the full picture of Mona Lisa, and uniquely so, right? It will be different from if you give a picture of Shah Rukh Khan or something like that. But so therefore, all these different initial conditions, which right here, which represents partial versions of one pattern, right, are very close to the original pattern. So therefore, imagine that the network starts from any of these points and goes to this final state. Same thing happens for other states also. So this kind of a network with this kind of dynamics, can be made to behave like a memory, or more specifically, an associative memory. But it's okay. So that's the intuitive picture. Now the question is, do we actually know that the network behaves like this? So we are just saying it will be nice if network behaved like this. But do we know that the network behaves like this, and how do you make it behave like this? So for that, we invoke a concept called an energy function. So in case of an MLP, we had an error function. So in case of MLP or a deep network, we had an error function. So this is the error of the output error. So this is output error function. And the network is doing during its training, right? Network is this is error function. The network is doing gradient descent. So in the weight space, if you start from anywhere nearby, you land in the nearby minimum. So these are called local minima. We studied all this in the previous topic. So so these local minima are the minima of the output error function, and then you land in one of these minima in the weight space during the process of training. In case of a Hopfield network, the error function, you don't have an error function, but there's an energy function, which is a function not of the weight space, but of the state space. This is a function of the state vector V, right? And then here also you have multiple minima. And if you start from some point, let's say here, you do gradient descent and land in the nearest minimum, right? And if you start from anywhere here, you'll land here. So similarly for other minima. Now these minima of the energy function act like memories. Okay, all these points act like memories. And so the memories that we saw here in the picture above, in the sketch above, the memories that we are talking about here are the same. So these points, these stable states, are actually minima of an energy function V. So now the question is, how do you construct such an energy function? Right, given that the update of the Hopfield network is governed by this equation, how do you construct an energy function such that as a network evolves following this kind of update rule, it will be actually going down a certain energy function and landing in a minimum, in a local minimum of the energy function. Okay, so the energy function that was proposed by Hopfield looks something like this, and it's actually inspired by the physics of magnetic materials. So he basically saw an analogy between magnetic materials and brain, and thought of a neural network which has memory properties. Because magnetic materials are popular for one reason for us as computer scientists, because that's what is used in a hard disk, in a computer hard disk. Right. So I'll talk about that energy later a little bit in more detail. So if you look at this expression, it is so it has a quadratic. It's a quadratic expression in terms of v, in terms of the state vector v. Actually, I'll come to this in a approach it differently. So I want a cost function. I want some kind of a function which goes to a minimum, and no, I'll come back to this. Okay, so this is the energy function. It is given as there's a double loop going over the weights Wij and the states Vi Vj, and there's a minus half factor in the front. Now we need to show that if you update V, right, following this update equation, this function always goes down. So how do you show that? So the thing is, when you update V, so I have some interesting situations possible. Let us say I'm updating the ith state of the ith neuron. When you actually apply this equation, it may so happen that Vi initially, that is Vi at t and Vi at t+1 could be the same. So then it's not interesting because nothing is changing. The network is probably converged, or that step is not interesting because nothing is changing. But imagine a situation which is more common where Vi at t is different from Vi at t+1. Okay, so then the energy function also will change. And so let us consider that situation. Okay, so when Vi actually changes, and the change can occur only in two ways. So Vi can change from in two ways, either -1 to 1 or +1 to -1. The only two ways in which Vi can change. So when that happens, right, take this delta Vi out of this whole expression. Okay, and you get this expression. And here we are assuming that, which is a very important assumption, Wij is equal to Wji. Okay, this is called the symmetry condition, which is essential for this result to be true. So we get this expression out. Now you can easily see that minus delta Vi is equal to 2 Vit. So how is that? So let us look at Vi at t, Vi at t+1, and delta Vi. Now delta Vi is given as Vi at t+1 minus Vi at t. Okay, so there are only two ways in which this transition can occur. Because first of all, we are assuming that there is a transition. We are not looking at no transition cases. So if Vi at t is 1, Vi at t+1 is -1. So then this will be -1 -1, so that's equal to -2. And if initially Vi at t is -1, this will be 1, and this will be +2. So you can easily see that this is equal to -2 of Vi at t. Okay, so this expression is equal to -2 of Vi at t. So that's what we are using in this equation. So minus of delta Vi is equal to 2 of Vi at t. So we need that. So when we do that, then we can actually do plus or minus of, so we'll do plus 2WII VI square minus 2WII VI square. If you do that, now VI square is just 1 because VI is plus or minus 1. So this is what is you see here, this term. This term can be absorbed inside. Okay, and so because what happens is when you take this delta VI out, the II term disappears. Okay, so therefore you have the condition I is not equal to J or J is not equal to I. So to put back the II term, we need to make this substitution, or we need to add 2 WII VI square and also subtract 2 WII VI square. So if you do that, again you get this. Now look at this expression. Now this you can, so 2 VIT times this whole thing. Now you can see that, so first of all, it is assumed that WII is greater than 0. That's a given information. So this part is negative. If you look at this part, the VI at t plus 1 is given as sigma of the summation, right? J goes from 1 to n, Wij Vj at t. So that's what you're seeing here. Okay, so VIT plus 1 times VIT. So obviously VIT plus 1 VIT should always have opposite signs because we were taking the case of only where there is a transition. So this product is always negative. So this is also less than 0. So this is less than 0, right? And this is also less than 0. So on the whole, delta is less than 0. So therefore, right, or equal to 0. Otherwise, what will happen is once you reach a stable state, Vi will not change. So therefore, delta E will be 0, right? So therefore delta E is either 0 or negative, and E should be bounded because W's are all finite values, and V's can only take two binary values, plus or minus 1. Therefore, E is bounded. So delta E is either negative or 0. So therefore, you can show that E will always converge. The update will always converge to a minimum of E. So you are basically by doing this, following this update rule, the state evolves towards a local minimum of this energy function. Okay, this energy, it's called energy function because in the corresponding magnetic systems analog, this expression is actually the energy or the Hamiltonian of the magnetic material. I'll talk about that later a little bit. Okay, so that sets the stage, right? We can see how you can have stable states, right, in an equation which is governed by this update rule. But what we want is, how do you make, so we have all these stable states, we can divide the whole, right, state space into different regions, and you can make the network go to certain states in that thing. But the stable states of the network should be our memories. That is, whatever you want to store must be at these locations, right? So, and these points are determined by the weights because where the network converges is all somehow encoded inside the weights. So I need to be able to manipulate my weights in such a way that I can store some patterns, some vectors. Right. So how do you do that? So for that we need a learning rule. So let us look for such a function. Suppose I want to store a vector, a binary vector S, which is where the ith component is Si in the network. Now I must do it in such a way that the energy function E must be minimum at S. That means at V equal to S or S equal to V, right? The energy function should be minimum. So how do we do that? Consider this expression E equal to minus 1 by 2n times sigma Si Vi, right? So this is dot product of S and V square. So what's the logic of this? So since all the vectors are normalized, that is, right, since the individual components are all ones and minus ones, they all have the same length. So they are normalized. The length is root n. So they are basically rotating on a kind of a sphere of radius root n. So if you take a dot product, when S equal to V, the dot product becomes maximum. Or if you take a minus sign in front, when S equal to V, the dot product becomes minimum. Now take a square of the dot product, which where again the same results are valid even if you take the square, because the dot product goes to a maximum. All right, even the square of the dot product goes to a maximum, and the two vectors become the same because they're normalized. Now expand this expression. Okay, so you have sigma I SIBA, square of the whole thing. So if you do that, you take sigma here, take sigma SIBA, multiply with sigma SJVJ. I'm just using two different indices. If you do that, then you get this expression, right? And this is actually identical to the form of the energy function which I've given here. The only difference is here I'm using the weight term. Here the same part, that coefficient, is now a function of the pattern which I'm trying to store, which is S. Okay, so that means the weight is equal to 1 by S of SISJ. So that means if I want to store a pattern whose pattern S, then I need to construct the weight such that the ijth weight, Wij, is equal to 1 by n times Si and times Sj. Okay, if we do that, then that vector becomes a minimum. That state becomes a minimum of the energy function. So if I start from some randomly anywhere in the network, it will go to that state. And if I want to store multiple patterns, right, I just have to do the same. So multiple patterns means I have SP, S1, S2, S3, SP, right? I do the same thing independently for each pattern and just add them up. Okay, I get a weight matrix, and in that weight matrix, you'll have all these patterns as stable states of the dynamics of the network. So this is how it works. So let us break here. I'll show some examples in the next class, and then we can proceed and to look at the biological relevance or biological feasibility, right, of all these ideas. Okay, so let us meet on Friday. Thank you.